Thank you. Thanks for having me. Okay, yeah, so please ask questions. Happy to answer and be interrupted. If you put in on a chat the question and I don't answer, please speak up because maybe I'm not seeing it. I see only my slides. Okay, so today I'm going to talk a little bit about our work on LLM inference with vLLM in particular, and also I'm going to mention SGLang, but mostly will be about vLLM. And, both projects started at Berkeley. vLLM was first 2023, and then SGLang, the paper was 2023, but what I'm going to talk about today was mostly 2024 because I'm talking about the backend, the inference engine. And as we speak today, at least with respect to GitHub stars, which is you can take that metric with a grain of salt, they are the top two inference engines, open source inference engines. Now, to provide, I mentioned to you, I'll speak mostly about vLLM, but to provide you the context, more context, the SGLang was, if you look at the paper, was initially thought to have a co-design between the front end and the back end. So you have also a language, a library on the front end to make it easier to more efficiently use the GPUs, in particular to share the prompts, whatever the prefix from the prompts and things like that, and also has a backend, and the backend it's like a classic inference engine. In time, SGLang started to focus more on the backend, on the inference engine, and initially was a simplified architecture compared with vLLM, and was mostly developed on XAI. But it's each of these inference engines are growing in popularity. They are actually arguably converging. So I hope they are going to converge at some point. But anyway, let me just. So this talk is about the challenges. It's actually, and the challenge, one of the way to formulate is that efficient use of KV cache, the key value cache. And then I'm going to talk about the two techniques, in particular PagedAttention, which was the core of the vLLM paper, which aims to reduce the KV cache fragmentation and obviously increase the usage of KV cache. And RadixAttention, which increase the KV cache sharing. So it's again, it's increasing the efficiency of using the KV cache. And then I'm going to talk about vLLM v1 re-architecture, which is happening as we speak, because I thought it will be interesting to see, because it captures some of the lessons learned from the previous designs. So when we started again, it was started in 2023, we started the vLLM, and obviously the problems then, and even today, is that there is a growing number of large language models and the growing workload, and these are very expensive. Very expensive to serve a request. And it was then, and it still is today. So large language model, at that point, we are talking about high-end GPUs like A100 and H100. And even for a Llama 13 billion parameters, an A100 can only process at that time a few requests per second, right? And I'm saying that this is also true today because as you've seen the GPT 4.5, the cost is very high. So yes, the smaller models and the previous models, the cost drop significantly, in some cases 10x or even close to 100x over 1 to 2 years. But at the same time, people release more and more powerful models, and the cost of the high-end models doesn't really decrease as much. Okay, so first, again, I'm sure that almost everyone here in the audience knows this, but let me still just to be on the safe side. So everyone, again, and I am maybe it's just recall that how this LLM query processing are working. So basically, you generate tokens sequentially, right? One at a time, right? You get a prompt, you compute the embedding from the prompt, and then you are going to generate the next token and the next token, always looking at all the tokens before it, right? Now, the main challenge and why you have this very high cost is because the throughput for GPU's throughput for serving this request is low, right? Low throughput, high cost. And obviously, as everyone knows, the reason for that it's one token generating one token at a time doesn't use GPU parallelism, right? It's the GPUs are most effectively used when you have multiply fat matrices, not a matrix by a vector or thing like that, right? So what is the solution, right? Okay, so you have one request, you generate one token at a time, very low GPU utilization. So how you increase it? Well, obviously, one way to increase it, you can process multiple requests at the same time, right? You can have a batch of requests. But then, if you do that, you soon run out of memory. And why? Here is why. First of all, this was A140 gigabytes. This was when we started the development of the vLLM. This was kind of the state of the art. And for a 13 billion llama models, you have parameters. You need for storing parameters around 26 gigabytes, 2 bytes per 16 bits per parameter. And then you have this KV cache, which is basically the working memory, and the all other is activation and things like that. And that KV cache was around 30%, parameters occupy 65%, and the others is probably 5%. So what is the problem? The problem is, again, remember that for a token to generate a token, you need to use all the tokens before it. So you need to store these tokens. You need to store all these prefixes. And then each token, you need to store not the token, but the embedding of the token. And a token embedding can be pretty large, like 1 megabyte, right? So one request alone can have several gigabytes. So you just can store a few requests in the KV cache, process a few, which means that you can only process a few requests at the same time, right? So that's why the KV cache is a bottleneck. So at the time I developed vLLM, this was the memory management in the GPUs was pretty basic. You basically you store the sequence of tokens contiguously in memory space. And this was convention in traditional deep neural networks. And you pre-allocate the space, because if you need to allocate, if you need to store all the tokens sequentially, then you need to try to figure out how big was the entire request, so you store enough. You allocate enough, because otherwise you wouldn't be able to store these tokens sequentially, the embeddings. Right? And this causes a bunch of fragmentations. So say the request A, its artificial intelligence is, so now first it just, you pre-allocate, say, 2000, assume the request size, including the prompt, is 2048, so you pre-allocate all the slots. Obviously, this results in internal fragmentation because you are going to over-allocate, right? So if the request is output is going to be much smaller, say 100 bytes, you are going to waste all the other memory you have allocated. Now, things are more complicated, right? Because we have another kind of reservation, fragmentation, as you call reservation. So say, you know, and the reservation are the tokens you would need to complete the request, but you haven't generated yet, right? So what this means is that even if you know the length of the request, say you know the length of the output, it's 100 tokens, okay? And you allocate 100 tokens, right? No more. It's still not the optimal use of memory because as you start, yes, you allocated 100 tokens. Yes, you are going to use 100 tokens, but you are not going to use them from the beginning, right? Initially, you are going to generate the first token, so you use only one token, 99 are still unused. Then you generate the next token, yes, you use two now, 98 are still unused, and so forth, okay? So still a lot of wastage, okay? And then you have external fragmentation because for different different requests, you may allocate, you may pre-allocate different different sizes, right? And if you don't allocate the same size for each request, then you are going to have gaps, right? Say in the simplest case, you have only two types of requests, right? And one you allocate 2,000 bytes, 2,000 tokens, and the other one 1,000 tokens, right? Very simple. You can still end up with a case in which you have a lot of gaps of 1,000 tokens. So you have 10 gaps of 1,000 tokens, but now I need 2,000. And because I need 2,000 tokens contiguously, I cannot allocate, although it's enough free space in memory. Right? And this is pretty bad. So here it's about in this case, about what is a wastage from different kind of fragmentations, internal reserved and external fragmentation. And the only thing you need to look here is green part. So the green part is basically saying how much from the entire KB cache you are really using, and how much is lost due to fragmentation. So, and this was Orca, that was a state-of-the-art model at that time. And you can go from 20% to 38%. And 38% is when you assume that you know a priori the length of the output, okay? So even if you know the length of the output, it's still the best you can do is 38%. So clearly it was an upper bound for those technologies, okay? So now I'm going to talk about the page attention, and which is introduced by vLLM. And just to be very clear, you know, page attention, this problem is not new, okay? This was everyone who took an operating system class knows about it, okay? It's like this is about memory allocation, right? And how do you solve this? And the virtual memory. And how do you solve this problem in operating systems? Simply, you just basically allocate only fixed amounts of memory, pages, fixed size. So this reduces the external fragmentation, actually makes it zero, right? Because every unit of allocation is the same size. And the only problem now, and also it can reduce the internal fragmentation, because the internal fragmentation it's upper bounded by the size of this page. The biggest problem now you have that from the application perspective, the memory is no longer contiguous, right? Because you have to allocate the pages wherever they are available. And to give the illusion of the application of a contiguous memory space, you use this kind of indirection. You have an indirection, a table, a page table, okay? That's the main idea, and I'm going to show you here how things are going. So you have a logical view of the memory, and then it's a physical view, right? The logical view is what the application sees, and the application is going to continue to see that it's a contiguous regions of memory, right? So as you can see on the left-hand side, Alan Turing is a computer scientist, is contiguous, right? Okay. And you have this kind of notion of blocks, which is equivalent, which is similar with the notion of pages for the operating system, and a block has a fixed number of tokens. Okay. In the operating system, for instance, a page can contain 4 kilobytes or 16 kilobytes. The size can be here. It's a block in this figure, in this example, has 4 tokens, right? It's fixed size. Okay. And the block, it's a unit of allocation, right? You allocate memory in terms of blocks. So as you can see again, on the left-hand side is contiguous. On the right-hand side is not contiguous. These are physical memory, KB blocks. So, you know, the block 0 from the logical memory, it's stored as a block 7 in the physical memory. And then the block 1 is as block 1, also both in physical and logical memory. So how you map then, you just use this kind of block table, which is an indirection table. And basically you say block 0 is mapping to block 7 in physical memory. And in addition, what you are also going to say, this in the second column, you can see, it's also, you can say how many blocks are filled. And the nice thing here, and that all the blocks are going to be filled sequentially. So if the number of blocks filled in a block is 2, this means the first 2 blocks are filled, because remember that these models just add 1 token at a time, generate 1 token at a time. And each token is based on all the previous tokens, right? So this is table basically saying, you know, the block 0 is mapped to block 7, and all the tokens in that block are used, and block 1 is mapped on block 1, and the first 2 tokens are used, right? So now if I'm going to generate another token, in the logical memory, it's going to be stored contiguously. Also in the physical memory, it's going to be stored in the corresponding block, block 1. And the same with the next token. And finally, now the block 1 in the physical memory, it's also filled. You continue sequentially in the logical space with Renault, and now you have to find a different free block, in this case, block 5 in the physical memory, and you continue. Okay, that's it, right? And this paging, will notice that also enables sharing, because you have a common prompt. This prompt can be shared across different requests, right? Because in the logical space, there can be different, but if it's the same content, they are going to map to the same block in the physical memory. Okay. So what do you get? Well, this is what you get, right? Remember about the previous figure, which showing the fragmentation with vLLM, you can get the memory utilization up, 2.5 to 5x improvement, up to 96% from 38%. And again, the 38% assumes that you have an oracle which knows how long is each request. More realistically, it's improvement from 26.8% to 96%. So almost 4 times. And this translates in throughput, right? Because now I can have, 2-3 times more requests I can serve at the same time, right? And these are some numbers when we launch it. And TGI, it was from Hugging Face. And you can see for different models, you can have significant improvement in performance. Now, I mentioned to you that PagedAttention is very similar with operating system virtual memory. So, but there are some differences as well. So what are the analogies? You can think about the pages like KV blocks, reduce memory fragmentation, and you can share the pages across processes. And similarly, you can share the KV blocks across samples, across requests. What are the differences? One difference is eviction. With a virtual memory, you have to make room for a new page. And the memory, physical memory is full, you have to evict a page. What you do, you take that page and you write it on a storage, on disk. Okay? And now also in this, let me just, right. So there are 2 differences here. So one, which is the second point here, is that if you were to do the same thing with the blocks for KV cache, you'll write these blocks, say in the CPU memory or on another storage, right? And then get them back when you need them. However, it turns out that actually in this case, you can use another way to reconstruct these blocks you evicted. And that is you can recompute the blocks back. Again, because it's very clear again. You recompute the blocks by recomputing the embeddings one after another, right? So that's kind of cute. And it turns also that in many cases, recomputation is faster than storing the block, paging out the block on, say, the CPU RAM, on the CPU RAM and bringing it back. And why? Because a lot of this recomputation can happen in parallel, right? And GPUs are very parallel machines. The other thing, what happens is that it's again because this workload is, we can specialize our technique for this workload. In general, for instance, in operating system, pages are treated pretty independently, right? You are going to evict a page which was not accessed for some time, but there is no relationship between pages other than that counters about how many times or when was the page accessed. But in this case, because when you need to compute the next token, you use all the tokens before that. Well, if you evict some of the tokens in that prefix, you can evict the entire request, right? Because if I have all the tokens but one, I can still not generate the next token, right? So there are this kind of the differences compared with virtual memory and operating system. So PagedAttention has been quite successful, has been used by many, it's actually in virtually every inference engine today for large language models. Okay, any question? So next, let me talk about RadixAttention, the second techniques, and this was a technique which was developed in SGLang. And this is a little bit about sharing. It's a KV cache reuse. Okay, so in many cases, you have requests which are subsequent request, they use a prefix from the previous one, or they share the prefix with previous ones. So one case, in this case, it's multi-turn chat. So in multi-turn chat, for the next iteration, you feed the LLM with all the history, all the previous interactions, right? So so just reuse the entire prefix, right? The other thing is about when you use, say, a few short examples, right? So basically, the prompt in their case contains a few examples, so it's pretty large. And you are going to present that prompt with those examples before asking your question. Maybe it's a math problem or something like that. So it's again, all these prefixes can be reused, right? And the other one, there are many techniques, like even to improve the accuracy of the results. So for instance, one technique is to generate for the same question, like for instance, programming. You can generate multiple solutions, right? And then you check these multiple solutions and you pick one which is better one, depending if you have tests for it. You can pick if it passes a test, or you can use simple majority voting to pick the most common one. But again, this is another example. You have a question which is a prefix can be used for many prompts. There is also an opportunity to do things in parallel, right? It's like you can generate, in this case, for this generate two tips for staying healthy, and then you can generate in parallel, for the first tip and for the second tip. Anyway, so this is the opportunity, RadixAttention, take advantage of this opportunity. And while existing systems at that time, they were just discarding the KV cache after request finishes, you just remove it. Everything about that request. In this case, you keep it, in KV cache, and you evict it according to some LRU technique, least recent used, which is classic cache replacement policy in actually operating systems. And basically you remove the entries, the blocks which are accessed, which haven't been accessed for the longest time, right? Because it assumes that if something has not been accessed for a long time, they are not going to be accessed in the future. Of course, this makes some assumptions about the access pattern, as we know that, for instance, for heavy tail distribution, that assumption is not correct. Okay, so now it's about maintaining a structure, an efficient structure. RadixAttention is about maintaining an efficient structure in the cache for these cases, right? When you have a share prefix. So here is one simple example. Say you are a helpful assistant, and then the user say hello, and you are a helpful assistant. It's a system prompt, right? Every prompt will be prepended by this, you are a helpful assistant. And then you have one interaction with the user, it's hello and hi. So now this generate a prompt and the output from that prompt. And now assume that you go to the next one, you generate, you have another interaction. So now the prompt is going, the output, the entire request store in memory is going to grow, because now it's a multi-turn conversation, and you are going to use a prefix from the previous conversation, and now you have another interaction within that conversation, right? So basically it's chain, you just append. But now, again, things can get more complicated, right? You are a helpful assistant, and then a user have a different question, right? Now, notice that when you are going to store this in memory, the tokens for you are a helpful assistant are common, right? To both of these conversations, right? And after that, they diverge, right? But still, even in this case, even with two different conversations, you are still able to share the tokens for you are a helpful assistant, right? And things get more complicated. And, for instance, here, you are going to have like another one question to have a conversation with 3 interactions, 3 questions, 3 answers, and then you can share that. And this is what it shows here. These questions, imagine here, this is about multiple shot examples, right? So here you give a few examples and then you ask your question, right? So the prompt, like we mentioned in the previous examples, contains this, all these examples, and then you use this to ask different questions. Again, the prompt can be, the prefix of this can be reused, right? And as you can see, the radix attention and is like radix trees. Try to optimize and to minimize the amount of replication and to maximize the sharing of the prefixes across all the requests. And at the end of the day, again, it's like some of those suffixes, right, in this tree or leaves, with their associated tokens will be evicted. Which one are going to be evicted? The one which have been not accessed for the longest time, right? And if you do that, these are results from 2024, you get much better results here. It's about, these are the throughput, and SGLang, it's orange. And at that time, performing significantly better than vLLM at that point with this new technique. vLLM didn't have this technique at that point, and TensorRT LLM, another popular inference engine from NVIDIA, okay? So for the next few minutes, if there are no questions, let me go a little bit about V1. So right now, it's a major revision of the V1 RLE architecture. And what are the goals? It's again, it's like, it's like you develop the system, but things are very in a very dynamic environment. A lot of things changes. A lot of your assumptions may be invalidated. Things you never thought, you didn't anticipate, you have to implement. So the code is growing. It's like you accumulate a lot of technical debt, right? So the main goal with this V1 re-architecture is to make it much simpler and easy to hack the code base, and provide higher performance, of course, with very little CPU overhead, and also to combine, now that you know all these optimizations, a lot of more optimizations than when you started to design the system. Now you rethink about how you can integrate in a much better way all these optimizations. Okay. So some of the things remain unchanged, like GPU kernels, the models you are supporting, user-level APIs, but some of the things change, like scheduler, memory management, and so forth. In particular, I'm going to go over 4 changes. Some of them are more or less obvious. Some are a little bit less, but all of you'll see common sense. When the first is optimize engine loops and IPA server, and this is make sure the GPU is not stalled, right? Obviously, right? You don't want to waste GPU. GPU is your most expensive resource. You better utilize it. And in this particular, in a previous case with V0, was a pretty basic design, and it was possible to stall the GPU in a variety of ways, but pre-processing, like converting JPEG images into in tensors, like tokenizing outputs, and HTTP request handling, because these are handled by CPU. Okay, so basically, you are going to do all this work on the CPUs, and you are going to invoke the GPU. Okay, so it happens sequentially. So what is the solution here is to have, obviously, it's a trivial one. You have two processes. One process for the front end to handle all this pre-processing and post-processing, API servers or HTTP processing, and then process one to handle the actually the inference, right? And it's not blocked because while now process one is going to process the previous, so let's put it this way. So the request comes, it's handled by the CPU, and after it's handled by the CPU, it's handled to the process one, to the GPU to make the inference. And while the GPU makes inference on the first request, the CPU handles the second request, right? So you are pipelining and overlapping the CPU processing with the GPU processing. This is basically what it is. Then it simplifies scheduler. Actually, here it was, we have a synchronous single-step scheduler, and it was quite complicated before. So you have, for each batch, you need to, you are going to have different ways to decide how many tokens from each request you are going to process. Okay. And so what the new scheme provides, it's very simple. Basically, it's having only one construct. So here you make the difference between prefill, decoding, and things like that. Here, there is no difference. And basically, the only thing you need to do it is basically to say how many tokens you are going to process, right? That's it. You have number of computed tokens is 0. All tokens you are to be processed, is in this all tokens ID you have, in this case 5. You can have a prefill, and you basically say, okay, I want to be processed the number of tokens to be 5, and then that's the only thing you need to say. You don't need to say that, oh, this is a prefill phase, this is a decoding phase, nothing like that. You just give 5 tokens, you take care of them, right? And then for decode, you give 1 token, right? Generated, right? You can also do, like, for instance, chunk prefill, right? Instead of in chunk prefill, you are going to provide chunks. Even if you have a large prompt, you are not going to pass the entire prompt. You can provide chunk from a prompt. And why don't you want to pass the entire prompt, even if you have it? Because you want to process multiple requests in parallel. So you want to process a little bit from each request. So in this case, you are going to say, okay, the chunk is 3. I'm only going to process 3 requests, right? And you can also have the prefix caching. If you already have in the memory this 3, you automatically, you initialize number of computer tokens to 2, and then you are going to see how many more tokens you want to process. Okay, so basically the TLDR, this seems maybe more complicated than it should be. Well, now I realize when I tell you, it's basically before you have you give the engine semantics about this is prefill, this is decoding, this is I want to do chunk prefill, and so forth. So all of this complexity was lowered into the engine. Right now, it's much simpler. The engine, you only give, basically say, you have only, for each request, you have only 2 variables, number of tokens which have been computed so far, and number of tokens I want to schedule. That's all, right? And the complexity about what you are going to, how you are going to decide which number of tokens should be scheduled depends of whatever you want to implement. Chunk prefill, classic prefill, and things like that. Okay. And there are many things about the scheduling which are going to need to improve. Now it's just first come, first serve. So we are talking about priority-based scheduling, fair scheduling, and things like that. The clean implementation of distributed inference is another thing we try to do it. So this is obviously, you have a scheduler, and vLLM has one scheduler for all the GPUs on the same node. Okay, each worker, you can think about each worker, it's a GPU. And it has different stages. And in the previous implementation, you are going to have, if you have a model which runs on multiple GPUs, you have to broadcast the tensors in some sense for the models, the whole input tensors to every step. So we got rid of that. We have also those two processes here, if you remember. And basically, we broadcast at the top. So we broadcast the basically Python data structure, which are much smaller than the entire tensors. And because tensor is after you do the embeddings. And at the same time, you also can do diff, right, on this data structure, the Python data structure, so you can only broadcast the differences. So it's much more efficient, okay? And the final optimization, which probably is the most interesting one, it's today you have a CUDA graph for the entire model, right? So attention and do everything in one CUDA graph. The pros are obviously minimal CPU overhead in model execution, but limited flexibility. And the CPU cannot do anything, cannot interfere here to do some smarter things, right? So also increase the development burden, because if you want to modify something, you need to modify the entire CUDA graph. So what we are using, which is a new, features for some time now, but it wasn't early on, it's piecewise CUDA graphs. So you are going to have multiple CUDA graphs. You are going to split in multiple CUDA graphs. And for some of these layers, like attention, you can use PyTorch Jigger, right? So you can use the CPU, right? And you may ask, well, why would you use that? I'm giving you an example. If you want to do sparse attention, right? If you want to do sparse attention, the CPU can do it much easier, and it's than the GPU, right? Of course, for GPU, it's going to be very complex to how to do it, right? This is beyond matrix multiplication, right? So, and also you have no restriction in shapes, and you can, and it turns out that if the model is large enough, say it's over 8 billion parameters, the overhead is pretty minimal, right, to go to the CPU. One example can use this is cascade attention for system prompts. Again, I'm talking about the system prompts. The system prompts can be large. And now, what cascade attention means is that you can, I talk about reusing the prefixes for different requests, right? If they share a prefix, you are going to reuse it. However, what it was hard to do in the past is to use to share the prefixes across requests in the same batch. And this is what cascade attention it is, right? You have many requests in the same batch. All the requests have the same system prompt. Now you can, using these piecewise CUDA graphs, you can share the prefix even across requests in the same batch. Okay? And this shows you some performance improvements. You can have the performance improvements, 50% throughput increase. Okay? Why? Because you use them now. Again, KV cache is used more efficiently. You don't need to replicate the embeddings for the request, for the system prompts for the request in the same batch. And there are many other cases. You can do. We are working on offloading the KV cache to CPU memory, to disk, sparse KV cache. I mentioned to you brand new attention algorithms you can implement, much more flexible. These are some early results. Again, I'm kind of run out of time. And this is for Llama 3, 8B. And the TLDR here that you see on the left-hand side, V1 can provide significant improvements over V0, right? And this is what you see, time to the first token and time to per output token, which is lower the better. You see the query per second, it's on the right-hand side, then time to the first token, it's on the left-hand side. And, sorry, not on the y-axis. The blue, which is V1, it's lower, which is better. So in summary, the LLM inference, it's a rapidly growing workload, no question about that. And one of the key challenges of improving the efficiency, improving the throughput, lowering the cost is efficient use of KV cache. I presented you two techniques, PagedAttention and RadixAttention, which are coming from two different systems we developed here. And vLLM and SGLang right now are very popular both and have overlapped in development more and more and are increasingly converging. Thank you.
Thanks so much. And now questions.
I'm happy to take any questions, obviously.
I can start. In the previous slide, the throughput seems sublinear. The data set used here is chat or something that actually shares the prefixes?
Yeah, share GPT. Yeah, we use share GPT, and this is, yeah, I should have provided more details. Yeah, you do the sharing. And there is another thing, you see this 8-step scheduling. This was in the early version of V0 of the version of vLLM. After each token, you have to test whether it's, you ended generating the entire output. So it's an end of output token. So after each token, you have to do it, and then you have to go through the CPU to check that. So that kind of context was expensive. And 8 steps is kind of overlapping, checking with generating tokens. So you generate tokens ahead, and I'm going to, to test. I'm a little bit behind of testing, but I'm testing in parallel. So in the worst case, you are going to generate just a few more tokens, but the throughput will increase because the checking and the generation will happen in parallel. But to answer your question, yes, it's quite a bit of sharing here happening.
Hi, Yang. Good to see you. Can you hear me? Hello?
Yes.
Oh, okay, great. So since you mentioned two works here, the PagedAttention and RadixAttention, and you see that the difference with traditional memory, virtual memory, is really it's more paged based. I think it's actually page-based give you more efficiency, but and also like more flexible sharing, not only on the prefixes, but also in the middle of pages. So I wonder if you see any further improvement on these two attention schemes.
Yes.
Because it's fundamentally limited by like the way KV cache is generating models today. Yeah.
I think the Radix obviously is working now with KV cache, and actually there are other. Actually, vLLM using a variant of that, which is hash attention, which is doing, I think what you are suggesting, that sharing at the block level, so page level, so to speak. And so, but I think that, in some sense, Radix attention is kind of optimal when it comes to sharing, right? Because it's very fine-grained, right? You maximize the sharing of the prefixes.
Yeah, right? But there's assumption that you have to share prefixes, right? What if some of the instruction are in the middle of your request?
I see. So you are saying that what happens if you want to share something in the middle?
Yeah, because if you look at virtual memory, it's like any redundancy in the page are useful. But I understand why Red is coming this way, because it's heavy cache, right?
It's very, totally. I see. I think it should be possible, but you need to, if you do that, you need to live with some. Okay, one way you can, one case in which you can do it, if you have new attention mechanisms like window-based attention. Okay, in the window-based attention, because in the window-based attention, you are going to, in the pure ones, which, works okay, but not great, you are just going to need the latest tokens, right? I think otherwise it's a little bit hard because you need to be able to share something in the middle, but the prefix to not be the same. But whatever something in the middle, it has to be generated based on the prefixes. If the prefixes are not the same, it's very hard to figure out how the middle will be fine. Okay, I think where this could happen, though, it's in more diffusion models and in video, text to video, and text to image, right? Which you have some locality, right? And I think in that case, it happens because you linearize the image, right? And, row by row, so to speak. And then between, say, for instance, between different, in a video, from one image to another, you are going to have temporal locality, right? And there'll be some areas in the video which are going to be unchanged. So in that case, definitely you want to share those.
I see. I can ask another question. So you mentioned all the changes to V1 that makes the it's easier to adopt new types of optimization. I wonder if you see any obstacles on supporting different models, right? Since you mentioned diffusion model and so on. Do you architecture challenges there in the VOM?
Yeah, the architectural challenges are, with some of the biggest challenges are expert parallelism. MOE, a mixture of experts. Because you're just getting large, like for instance, if you want to, it's still quite difficult to be really to efficiently support something like DeepSeek. Because 670 billion parameters or 71 billion parameters, it's going to be distributed, and then you need to look at all this kind of different kind of parallelism.
But I think VOM already supports these different types of
parallelism. But what is hard? I'm telling you what is hard to do. Expert parallelism, right? Because the experts, it's very irregular traffic. And every token you can use different experts, right? So actually, that is problematic. Actually, in some sense, you see, the mixture of experts do not help you too much with the KV cache, because you still need to store all the parameters, right? Because you don't have kind of locality between subsequent tokens in the worst case. So I think there can be, and I know that some research about, can you kind of force more locality? Like for instance, if I have only a subset of experts, maybe the most popular experts in the memory, I don't have all of them. And maybe, yes, a token, for each token you have distribution probability about which expert to choose. Maybe you don't have the first expert in memory. Maybe you can pick the second one. Is that good enough, right? So you minimize that. Or can you have more but this also probably need to be combined with training for different kind of requests, maybe you can have more a subset of experts, right? So you can have more on a per request affinity with the experts you are going to use.
But these new requirements can be built on top of vLLM, right? Do you
Yes,
see
you can build on top of the vLLM, but you never know until you build them whether
I see.
how efficiently are they are, right? Remember that all of this lesson we learned is because initially we thought, it's you design a system on the requirements you know at that given time, and now you have some lessons, and what you hope is that as you iterate, the number of kind of really new cases you are going to see is going to decrease in time, right? It's like, or they are not going to be as different. It's kind of convergence, but it remains to be seen.
Yeah. Thank you.
Okay.
High-level question about the convergence that you mentioned that you wish to happen with the SGLang. So I'm curious about like how do you see it and like when to use which?
I think it's I think that for instance, for the DeepSeek, SGLang had a head start because it was focused on DeepSeek very early on, models, supporting models. So in some sense, vLLM is only now catching up with that. So that will be SGLang. I think, for instance, for heterogeneous, compute, to build to different accelerators, vLLM, it's a strength of vLLM because from day one was sought to support multiple accelerators. I think that before V1, we'll see after V1, SGLang was easier to develop and to extend, also because it has fewer features. And when I say the convergence, it's like, like this was one thing, this was one thing I'm thinking, but now SGLang also start to add supported new GPUs and add more features, which it requires, so it's becoming bigger and bigger itself. And now, vLLM with the release of V1, which, is like, it's still an experimental now phase, try to simplify the core, right? So it's always, again, it's like, because both are open source, when you do something, and even if I build now a new system, I'll build a much better system because I've seen all of these things that happened before me, right? See what worked, what didn't work. Of course, the problem is building a new system is that it's a huge overhead in adding all the table stake features, right?
I have a question. I want to ask about the reasoning systems. Like, how do you see the challenges in the reasoning systems, like models that runs a chain of thought or whatever reasoning system compared to?
I will. Happy to. So after this question, maybe I can answer only one because I need to. I have a hard stop, unfortunately. So I think the reasoning is very complex. It's a very complex system because you need to do a lot of things. You need to do everything for data generation, model distillation. If you employ reinforcement learning, which many do now, you need to do rollouts. Rollouts needs to run the environments. You need to do training. You need to do inference. You need to do rollouts and execution. And environments can be a simulator. Environment can be obviously like a Docker image and things like that. And you need to orchestrate all of those. we need to orchestrate that asynchronously. Like, for instance, one of the common systems right now, popular systems for doing this test time compute is vRL from ByteDance, which actually is using vLLM and Ray, as another system we built here. But for instance, that is great, but when you try to extend it, you hit the bottlenecks, right? In terms of, for instance, it's too synchronous. You need more asynchronicity to use resources better, to overlap CPU, GPUs, processing, things like that. And I think you'll see a lot of, because it's still in flux, you are going to see a lot of evolution, both in the algorithms and both on the systems, on the system side, and in that space. And I can tell you that initially with Ray, RLlib was one of the main libraries in reinforcement learning. It was the most complex one by far, because many people, there are many dimensions to innovate on.
I see. Thanks.
Okay, yeah. Anything else? Okay. Thank you
Thanks
so much.
so much.
I really enjoyed, and you can send me other questions. Happy to answer. You know my contact. Okay. Thank you.